Hey everybody, I hope your exam preparation is going well. I just wanted to cover the last few topics of metabolism that I didn't get to do last week because you guys hadn't covered them in class yet. So, um, yeah, it shouldn't be like too in depth, especially because I don't think he's making you do like carbon tracking for the Krebs cycle is what I heard, but I'm gonna go over an example of that anyway. So, um, it shouldn't be too bad. So the first thing I wanted to go over was just pentose phosphate pathway because I didn't really want to make like a whole video dedicated to this because it's really long and a lot of the reactions in this are things that you've already seen before. I think that a lot of why it's difficult is just because, looking at it, it's very intimidating to look at. There's a lot of lines, there's a lot of carbohydrates moving around, and so I just wanted to explain like what it actually means. And so the way that I want you to think about the pentose phosphate pathway is like it's not a product or it's not a reactant and a product. It's more like a cycle in the sense that the TCA cycle is a cycle. And essentially what's going on here is that you have these starting materials. These are these five glucose 6-phosphates that you produce from the hexokinase reaction that we see in glycolysis all the time. And you're basically going to end up, at the end of this pathway, you're going to regenerate those five glucose 6-phosphates. The reason that the pentose phosphate pathway is run is mainly for biosynthetic purposes. So, like the immediate application is like, producing these ribose 5-phosphates over here, so that you can do nucleotide synthesis. And there's a lot of other applications of it as well, but that's like the main one that comes to mind all the time. And so the way this works is that once you have these 5 glucose 6-phosphates, you'll put them through these oxidative steps, where you're progressively oxidizing it. You have the lactone, and then you get the phosphogluconate. Once you get to 6-phosphogluconate, you're going to put them through this 6-phosphogluconate dehydrogenase. What that's going to do is it's going to make you these 5 ribulose 5-phosphates, and at the same time, we're going to kick off this CO2 right here as carbon dioxide. And so once we have that, we take 4 of them, we run them through this phosphopentose epimerase, which is going to turn them into an epimer of ribulose, which is xylulose 5-phosphate. The other ones are going to be isomerized, the other two, to ribose 5-phosphate. And then after this, at this point, everything that we do just focuses on, okay, we have these carbohydrates now. Let's, get them back to being glucose 6-phosphate. And that's what these next series of reactions are. So you've got, ribose 5-phosphate. One of them is going to go through this, transketolase reaction. We're going to add it to a glyceraldehyde 3-phosphate, and take them back all the way up this pathway to, being back to this glucose 6-phosphate. And at this point, it kind of just becomes pretty repetitive and very memorization dependent. And I'm not going to go through like every single reaction on there. You can follow the arrows either on this one that I've drawn. I don't know how well you'll be able to see it in the video, but you can follow the arrows on this one or on the diagram that he's got posted on Canvas. And you kind of just, go through and memorize like what transketolase does, what transaldolase does, and like, where glyceraldehyde 3-phosphate comes in. And I think the only hard part about this is like, you never really see, satoheptulose 7-phosphate or like erythrose 4-phosphate. You never really see those things in any other metabolic pathway. So just knowing how, like where those come up, and being able to recognize when you see them, just like, oh, this is a pentose phosphate pathway intermediate. But yeah. So that's kind of all I wanted to talk about that. And then the main part of this video was going to be the Krebs cycle. And actually, so a lot of people asked me in Action Center last week, if they needed to know the TCA cycle and the citric acid cycle for this test. So I just want to clarify that the Krebs cycle, the TCA cycle, and the citric acid cycle are all three different names for the same thing. So they're not three different cycles, those are the same thing. And TCA stands for tricarboxylic acid. So if anybody ever says like, oh, draw the tricarboxylic acid cycle for some reason, they're talking about the Krebs cycle. So yeah. And so the first thing I wanted to cover is just like why we care about this pyruvate dehydrogenase thing and what it does. So pyruvate dehydrogenase is like the link between glycolysis and the Krebs cycle. So glycolysis, we're going to produce these two pyruvate molecules. Pyruvate dehydrogenase is going to turn those into acetyl-CoA that can be used in the Krebs cycle, to generate more energy equivalents. And you'll see, like, once we actually go through the Krebs cycle, we're not actually going to produce ATP. We're going to produce one GTP, which is like an ATP equivalent. But the main, like, energy source that we're going to see in the Krebs cycle are all of the NADHs that we produce and all of, like, those reducing agents that we're going to produce and you'll see why that's important when you get to the electron transport chain. So pyruvate dehydrogenase is this big enzyme complex. It's gonna put in, a CoA. It's gonna put in an NAD plus, and it's gonna use these cofactors that it has: thiamine pyrophosphate, lipoate, and then FAD, to take your pyruvate to acetyl-CoA. And that this is the enzyme that he's probably talked about it, like the lipoate, and there's a lysine residue inside the enzyme complex that make up this dihydrolipoyl transacetylase hinge thing that like is able to swing between the enzyme domains and carry around the TPP and like the pre-acetyl-CoA molecule that you've got before it releases it. It just carries it around between the domains and lets them do their, catalytic activity on it. So yeah, pyruvate dehydrogenase, you're going to make acetyl-CoA from pyruvate. And then so when we actually get into the Krebs cycle, here is our acetyl-CoA that we just made. This is oxaloacetate. That's just floating around. So this enzyme, the first enzyme, is called citrate synthase. And it's called that because it synthesizes citrate from acetyl-CoA and oxaloacetate. So what it's going to do is it's going to take a water molecule and we're going to release our CoA and an H+. And so basically what we did is we got rid of like this part of the acetyl-CoA molecule and we stuck on 2 carbons to this oxaloacetate. So these are those 2 carbons right there. And so basically what we just did is we took a 4-carbon compound and we turned it into a 6-carbon compound, citrate. And because this is a cycle, and we're going to be going back to oxaloacetate eventually, the rest of these steps are going to be reducing the number of carbons from 6 back to 4. So once again, we took these 2 carbons, these are these 2 carbons, that this one right here, this carbonyl carbon, is this carbonyl carbon. And I'm harping on this a lot because there's a question like this on your action center that I'm going to go over, and this is a really good type of question for him to ask on a test, I think. So after you get citrate, there's this other enzyme called aconitase. Aconitase does this interesting mechanism where it basically recycles a water molecule, and it goes through this like cis-aconitate intermediate to make isocitrate. And it's called that because it's like it's a slightly different citrate. Essentially, we moved this hydroxyl group down one carbon. So yeah, that's isocitrate. Isocitrate gets run through isocitrate dehydrogenase. And because it's a dehydrogenase, we'll have NAD plus going to NADH because this is an oxidation, so we need to reduce that. And then we've also got an H plus that goes in and releases a CO2. And so the CO2 that we're releasing is this one right here. And so that's like our first carbon release. That's like, okay, now we started with a 4-carbon compound. We made a 6-carbon compound. Now we're back to a 5-carbon compound. And this one is called alpha ketoglutarate. And I'm pretty sure that this one is like a transamination cousin, or like a precursor to glutamate. I think that's how it works. So anyway, this goes through this enzyme called alpha ketoglutarate dehydrogenase. And what that's going to use is it's going to take in another CoA and an NAD plus, and we're going to get rid of an NADH, or not get rid of, but like this NAD plus gets reduced to NADH, but we're going to get rid of a CO2. And specifically, that's this bottom CO2 right there, because we've replaced it here with this CoA group that we put in. And so this is called succinyl-CoA. And once we have succinyl-CoA, we run that through succinyl-CoA synthetase. Which is kind of a weird name for an enzyme to be called that, because you would think that an enzyme called succinyl-CoA synthetase makes succinyl-CoA, but it actually goes the other way in this in the Krebs cycle, where we're taking succinyl-CoA and we're making something else from it. And so what this is going to do is we're going to use we're going to take a GDP and a PI, and we create GTP, and we release that CoA that we just put on. And so GDP and GTP is like an ATP equivalent in terms of like the energy that it's producing. And so this is like a pretty significant energy payoff step for this cycle, but this isn't why this cycle is necessary. We're not running it just to produce this one GTP. We're actually running it to produce all of these NADHs, these reduced things throughout the cycle, because they're going to feed their electrons back into the electron transport chain. We'll get a lot more energy that way. Anyway, so this is going to, succinyl-CoA synthetase is going to make succinate. And one of the important things to be able to recognize about succinate is that this is a symmetrical molecule, and that's important for when you're carbon tracking. And I'll show you an example of that pretty soon. So succinate gets run through succinate dehydrogenase. Succinate dehydrogenase is actually a complex within the electron transport chain. And that's why we use, FAD and FADH2 for this rather than NAD and NADH, because these are more readily available there. And it just feeds the hydrogens and the electrons directly into the electron transport chain. So this is FAD, FADH2. And then so we're going to get fumarate. And once we have fumarate, we have this double bond here. So we're going to try to break that. And the way that we normally do that is with water, if you remember from organic chemistry. So this enzyme is called fumarase. And we're gonna put in a water, and it's gonna break that double bond, so we get malate. Once we have malate, we run malate through malate dehydrogenase. And we're going to oxidize it back to oxaloacetate. So to do that, oh, that's not very neat. We'll take NAD+, convert it to NADH. At the same time, we'll oxidize malate back to oxaloacetate. And once we get oxaloacetate, that feeds back into the beginning of the pathway, and then this cycle can keep repeating itself as long as there are acetyl-CoAs available to do that. So yeah, that's the TCA cycle. Hopefully that made it seem a little bit less intimidating than it looks like, because I know that this one has like a very bad reputation among the cycles that you'll have to memorize. And so this is a question that a ton of people asked me about last week, and I just wanted to explain it one more time just so that you have the explanation. So acetyl-CoA, let me copy this cycle over here actually so you can see it better. Okay. So acetyl-CoA, let's say that we label that, at carbon 14 at the carbonyl carbon. What that's going to look like is, so here's our acetyl-CoA molecule. So this carbonyl carbon is going to be labeled. And so what's going to end up happening here is that this is why I was like stressing the fact that like which carbons actually got put on the oxaloacetate. So if you remember, it's these two, and so if we have oxaloacetate, these two carbons are going to come and like sit on top of it right there. I should have drawn citrate, but here's citrate. Okay, so there's citrate. This used to be the methyl carbon of acetyl-CoA, and this is the carbonyl carbon of acetyl-CoA. And so this is the one that's labeled in citrate. And so once if we're looking at citrate here, and I'm saying like, okay, so I'm labeling this one, so this is labeled as well. I lost a CO2 here, but it's not this one, it's this one. So I don't really have to care about, what that CO2 does right now, but this one is still labeled for the time being. It's still labeled here. Now the important thing is that when we get to succinate is symmetrical. And so when succinate comes out of the active site of succinyl-CoA synthetase, we don't know which carbonyl is going to be labeled. We just know that it's one of them. So it could be this one or this one. And then so going forward in the cycle, it could be that one or that one, this one or this one, and then similarly this one or this one. And so he gave this like as a multiple choice question, like, after one after one turn of the cycle, oxaloacetate, so this one would have carbon 14 at, and so it's going to be either of its two carboxylic acids. Or so either of the two carbonyls of those, carboxylic acid groups.